Okay, so the project I'm going to be talking about is OpenKIM, the Open Knowledge Base of Interatomic Models, and it provides standards and infrastructure for making molecular simulations reproducible and reliable and so on, as I'll tell you. There are a variety of people involved in this. You can see a list of the PIs and the key collaborators in the project. Ryan Elliott and at the University of Minnesota with me was the technical lead. Ron Miller is the KIM editor. Mark Transtrom and George Karipis are co-PIs. And then in a related project where we're extending our work to chemical and biological force fields, we have Hendrik Heinz and Wampil Im from the Charm GUI project. And then I've listed some of the key developers, the core developers in the project. This project has been funded by the US National Science Foundation. And continues to be funded by them and is considered a core cyber infrastructure by the NSF. So I'll kind of go through what it is that KIM is, focusing on sort of some of the main capabilities of the project. It was established in 2009 with the goal to improve molecular simulations in several key categories. So first one is portability. We developed an application programming interface standard that will allow any interatomic models to work seamlessly with any simulation code that conforms to the standard. And I'll elaborate on each of these. I'll just give you kind of an overhead now. I'll elaborate on them. So portability by developing an API standard. Usability to make it easy for people to access potentials that they would like to use with their codes. Web queries, so sort of REST APIs that allow us to access properties that are archived in the system. Reproducibility, so we do that through warehousing of implementations, actually the actual software associated with the interatomic potential with version control, and DOIs to enable persistent identification of these over time and being able to access a particular potential. And reliability. So a lot of what Yuri has been talking about, standardized protocols for property computations. We also do something called code verification or verification checks that I'll tell you about. Methods for selecting an IM or an interatomic potential for an application. So again, along the lines of what Yuri described. And then uncertainty estimation for IM predictions. So those is sort of the overall scope of the project. So let's start with thinking about portability. So prior to KIM, interatomic models, IMs as I call them here, were simply functions that were implemented directly within a molecular simulation package. And so you see here on the right an example of a Fortran 90 implementation of a Lennard-Jones potential, or a pair potential actually in general, and on the right the C++ implementation. And that would be implemented somewhere in the simulation code, a code like LAMMPS or DLPoly or IMD or whatever code you like. The problem with this approach is that there's no easy way to port implementations between codes. So if you have your own code or you use a different code, you have to go and dig in for the code, figure out exactly how it's interfaced within the code you're taking it from. So very difficult to do. It's difficult to track changes to the code itself and to maintain its provenance. Many cases you don't know who put that code in. Since it's buried in a much larger code, it's difficult to track changes to this piece of the code, which is a particular potential. And there's no real way to specify versions of the code. So if you want to, say, 10 years later, refer to a specific implementation, a specific version of the code that you used, it's buried within this much larger code that may or may not be versioned and hard to know where your potential changed. And so KIM introduced this idea of the interatomic model as an autonomous computational unit that's separate from the simulator in which it sits. So we sort of have this picture in mind. On the left, you see the simulator. And by a simulator, we mean something like a molecular dynamics code, a lattice dynamics code, a Monte Carlo code, whatever you want, multi-scale code, something that uses an interatomic potential to do computations. So that's the simulator. And on the right is the model the green square on the right is the model. That's the interatomic model itself. And that's an independent unit that takes as input an atomic configuration, positions, species, charges, whatever is necessary to define that configuration. And then it gives you back energy, forces, and so on. And so what we've separated the potential from the simulator, and they communicate through the API that we developed, this KIM application programming interface. In the beginning of the project, way back in 2009, we sat down with many of the key model and code developers and hammered out an API that would be able to work with all of those different settings. And so the basic idea is that the simulator that can be written in any language that we support, which you see on the bottom listed there, the potential can be written in any language that we support. They communicate to each other through the API. So in fact, both of them are compiled separately. The simulator is compiled as an independent standalone program. The model is compiled and it's a dynamic link library. And at runtime, they interface and they communicate through the API. And what is actually passed between the simulator and the potential or the model is just a pointer to a data structure that contains all the information that the potential needs. And then the results are packed into that structure and returned. And so it's very lightweight because of that. No data is actually copied and translated. It's simply passing a pointer back and forth between the simulator and the potential. Now this API, we've spent many years developing it to be adopting API best practices, things like implementation hiding, loose coupling, minimal completeness, and so on, to ensure that the API is robust, easy to maintain, and easy to use. And so at this point, we're at version 2 of the API, and it's quite stable and works quite well. Okay. So that's the idea of portability. And by doing that, by creating this ability to create a standard that simulators and models conform to, KIM can provide support to a lot of different types of platforms that need that type of service. So for example, simulation platforms. So things like I mentioned some of the MD codes, DLPoly, ASAP, LAMMPS, ASE. All of those are conformed to the KIM API. We've worked with the developers on those codes and can seamlessly use interatomic potentials that conform to the KIM API within their codes. There are also support for finite element codes like Abacus, ANSYS, PHEEP, multi-scale codes like quasi-continuum method, lattice dynamics codes like GULP, the NanoHub system, and others that I'm not listing here. And so we think that this is very important because one of the things that we want is we don't want, say, take a code like LAMMPS that has a fantastic library of potentials. We don't want that to become a monopoly on molecular simulations. We would like to be able to, if you have an idea for a new code, maybe molecular dynamics, maybe not, maybe something completely different. Like we have a package that for doing stress analysis. If we had to implement individual interatomic potentials within each one of those packages, it would be very limiting in the sense of what we can do. But by having a standard like this, any code can use a whole repository of potentials that are available. So we feel that's very, very important for innovation in the field. In addition, the KIM API provides infrastructure for potential fitting packages like CLIF and PotFit, potential comparison tools. So we heard about Yuri, about the ICAMS project, atomistic tools for comparing different potentials, PyIron. We have our own OpenKIM comparisons where we use our own potentials to do comparisons. And then analysis tools. So I mentioned this MD Stress Lab code. This is a package that we developed within my own group for stress fields. So if you want to use this to look at a stress field in a configuration, you simply load in a configuration, load in a potential, and do the analysis and plot the stress field for your configuration. So that's the type of power that something like the KIM API provides. All right, so that was portability. The second one was usability. We want to make it easy for people to use potentials. To do that, we have basically worked to develop binary packages for the KIM API and for the library of potentials that we provide. We have them available now for all major Linux and distributions for Mac, and are currently developing it for Windows systems. What that basically means is you can see in the little code snippet here, on different systems, you use the native installation binaries to bring down the KIMAPI and the models. So you can see how you would do it in Ubuntu and Mac. Like in Mac, you would just do brew install OpenKIM models. And that will automatically bring in the KIMAPI and the library of all potentials that are in our system, which is 400 and something currently and growing. Conda, we worked with PyIron and making it work through Conda and so on. Now, just so you understand, this is not easy to do. Maybe some of you do, and you know what's involved in making your life so easy with packages, but it's hard work. First of all, you have, just so you understand what's involved, you have to structure your program according to what's called a file system hierarchy standard, which is how you need to design it so that it can go into a binary. You then need to build your package using a portable build system, something like AutoTools or CMake. We use CMake for our builds. You need to find an authorized packager with each one of these projects, and that's an actual human being, a person, that has to work with you in the submission process to the binary. It's sort of a trust-based system, and so you have to establish a relationship, and then you work with the packager, that person, to create packaging scripts that will build and install your program according to the conventions that each distribution has, which are all different. And then you have to keep this up to date, and so you have to maintain these distributions and push new versions and so on. So we've done a lot of that hard work to make our models available to the community in an easy-to-use fashion. Okay, so that's usability. Next is reproducibility. So Yuri alluded to that in his talk. They want to be able to tell somebody when they do a comparison what potential was used, or if you publish a paper and you use a particular potential, you want users to be able to reproduce your work, or you should want that. And so the way we do that within our OpenKIM system is we curate a repository of IAMs. They're subjected to strict provenance control and version control. Quality is enforced by a person. That's the KIM editor. That's Ron Miller at Carleton. Within our own system, each KIM potential is identified by a unique KIM ID, which is sort of human readable. There's what kind of potential it is, EAM in this case. NN, it's a nearest neighbor, EAM potential. Johnson was the author. 1988 is the publication year. CU is the species. And then at the end is a code that we use internally to represent the potential. And so MO says it's a model, an interatomic potential. This 12-digit number is a unique identifier, and the last 3 digits is a version. And so if somebody corrects something in the potential, if it's reissued, a new version is identified. Or if you extend the potential in some way, you either decide it's a new version or you fork a new potential if it's a major modification. Now, in addition to that, although these IDs that I say up here are permanent, they're permanent identifiers, still, in order to have something that's more, has the trust of the community, we also issue DOIs to all of our potentials. KIM is a member of DataCite, and using that authority, we issue DOIs to all of the potentials in our system. And that means that our vision is that people who use potentials in a simulation or in a publication will cite the potential. And so you see an example here, the potential employed was Johnson's nearest neighbor EAM potential, 1. So 1 would be the actual scientific citation for the content, but then archived in OpenKIM. And then you give the item 2 here says who developed the actual code that's in the system and what is the DOI. If you click on that DOI, it takes you right back to the page on openkim.org that has the potential, including the source code and everything you need to reproduce the exact simulation. An additional important thing, especially in our day and age, is that you also give credit to the person who developed the code, not just the people who developed the scientific methodology. Sometimes they're the same, sometimes they're not. And I think it's important to give people credit for digital content. I'd probably speaking to, preaching to the choir about that in this audience. Okay, and so okay, this is just highlighting what I said, that DOI points back to the original potential and allows you to reproduce simulations. Okay, reliability is sort of the last category. So we talked about portability, usability, reproducibility, and now reliability. So reliability is a lot more difficult. And we do that in two different ways. The first thing, which is sort of unique to the OpenKIM system, is we do something that we call verification checks. So we run the potentials through a series of tests that are not checking their accuracy, but are checking that they are correct in the way that they are operating. And we divide those into three categories, what are called mandatory verification checks, consistency, and informational verification checks, or VCs for short. So mandatory things are, we won't accept your potential if it doesn't pass these mandatory checks. Does it support the species it claims to? Does it handle unit conversion correctly? I didn't mention that, but KIM manages unit conversion behind the scenes for simulators and potentials. So is that done correctly? Does it handle domain decomposition correctly? Etc. There are other tests like this. Consistency are things like, is it internally self-consistent? So for example, are the forces that it reports consistent with a numerical derivative of the energy? That would be a nice feature to have in a potential. And we used to have it under mandatory until we realized that many potentials are actually pretty bad in terms of the accuracy of the forces they return for a variety of reasons. You know, they may do charge equilibration, which is done to some different level of accuracy and so on. So we move this to consistency and we provide a grade on that. You get from A to basically an F, using sort of the American system of grading A, B, C, and so on, to say whether your potential is, how well how accurate are its forces. Does it support translational, rotational invariance? You know, if you take a configuration and you rigidly rotate it, the energy shouldn't change, right? Assuming there are no external fields. But again, this used to be mandatory until we did it to hundreds of potentials and found that many of them failed, or not many, but some failed. And again, they fail for things like, a good example is again, charge equilibration. As you rotate, the numbers change and charge equilibration is accomplished to a different accuracy. And so these are things that are good to know, because you may bang your head against the wall, do a simulation, you know, where you have maybe molecules rotating in space and the behavior is weird. And it turns out it's because the charge equilibration changes every time the molecule rotates. And so these are things that by looking at the verification checks, you can know. And then informational. So things like, is the potential continuous? Does it have a smooth cutoff? Does it support inversion symmetry? Does it have memory leaks? Does it depend on optimization? Things like that. So that's what we call verification checks. Then another category of testing that we do are things more along the lines of what Yuri described, where we compute predictions. We compute material properties using what we call KIM tests. These are these protocols that Yuri mentioned. And one of the things that we have in our system is we define something called KIM property definition schemas, which clearly define what the property is, so that you can compare between potentials and you can compare to DFT and experiments in an automated fashion. And so if you say compute a thermal conductivity or thermal expansion or a gamma surface or whatever, what that means is defined in the sense of what exactly are the keys that you have to specify for that property to be defined. And we separate that physical notion from the algorithmic notion. So what Yuri calls a protocol is the algorithm by which you do it. You do this, you build a unit cell, you expand it until you converge, all that kind of stuff. That's encoded in our KIM test, but we also separately encode what is the physical property you're computing? What is the ensemble, temperature, pressure, you know, what is it? What do you need to fully define what that property actually is that you're reporting? And so I won't have time to go into that, but if you're interested, I can show you how we do that. And so with these, we now have, you can think of OpenKIM as a big repository that's full of potentials. It's full of these tests and VCs, and it's all automated. So now if you add anything new, if you contribute a potential to our system, or if you contribute a new test or a new VC, everything just automatically springs to life and updates the repository. So for example, what you're seeing on the screen now is if I upload a new verification check or a new test into the system, what it will do is it will automatically trigger a computation where it tries to meet that test with every single potential in our system. It can automatically determine if they're compatible or not. And if it is, it launches a calculation on the cloud that does the computation and feeds the result back into the repository. And then the flip side is that if you add a new interatomic potential, a new model into the site, it will automatically be run against all verification checks and then against all of the tests in the system to compute all properties that are relevant for that potential. That system is done using something called the KIM processing pipeline. I'm not going to try and explain this complicated diagram to you. You probably wouldn't be interested anyway. But what it is basically an automated framework to do what I just described. The things to point out is that we automatically manage dependencies between properties. So for example, if I'm computing a surface energy, I may need to create a crystal that the equilibrium lattice constant. I don't want to recompute the equilibrium lattice constant. So I can read that result in from a previous test. And that's indicated in the way you write your test, and all of that is automatically managed by the pipeline to make sure dependencies are run first and so on. And so we've just submitted a paper on this. If you're interested, you're welcome to take a look at the details of how this works. It uses something called Celery, which is a queuing system, and it's all cloud-based with workers distributed and so on. One of the things that I actually it's not on the slide, but everything that we do is done in Docker containers in a way that we can reproduce the work so that we know what versions are being done and so on, so that everything is done in a reproducible way. All of that is, these workers that I described are basically Docker containers that have their full environments encoded in them. Okay, so just to briefly show how this works in practice, this is what the OpenKIM.org website looks like. You can select a potential. There are many passes through it. I'm just sort of showing you a common use case. If you click on that, it'll bring you to a list of all the potentials. There's also a way of selecting. If I want to find nickel aluminum potentials, you can select nickel and aluminum, and it'll show you just those that support both of them. So this is a list of all the potential, or some of them. I didn't have room for all of them, but some of the aluminum potentials in the system. You see the KIM IDs. It tells you which simulators they're compatible with, any because they're portable in this case, and then a brief description, a brief title. And if you click on it, you go to something called the KIM model page. Each potential in our system has a page like this, which has all the information about that potential. At the top is metadata, things like the title, the description, which species it supports, a disclaimer. So one of the questions that Yuri got, I forgot who asked it, but was about, you know, the potential, the developers of the potential said it was developed for this, but you're showing all these results for it wasn't designed for it, so it's going to look bad, but it's actually not a bad potential. And potentials are actually developers are actually very worried about that, how their potentials are perceived. It's in some sense not fair to take a potential and test it against a whole bunch of things it wasn't designed for and give the impression that it's a bad potential. So we agree with Yuri that all potentials are good for something, and the question is what they're good for. And we take that into account in the way we do comparisons. But anyway, the disclaimer is one way for the developer to make their opinion known about this. And so there's no disclaimer on this one, but in some potentials it might say, this potential was designed for liquid metal structures and should not be used for other properties. And that disclaimer accompanies all of the comparisons that we do so that the developer has an opportunity to say that. Anyway, and then there's a bunch of other things where the content came from, who the author was, when it was published, the citation information that you can get in BibTeX format, including both scientific citations and the archival citations, the ID, the DOI, and so on and so on. Then if you go further down the model page, you get what we call the verification check dashboard. That's the result on those verification checks I mentioned. You see the grades are green is good, red would not be so good, or yellow, it kind of is a color scale. P means pass, A is a grade. So this thing, for example, on force numerical derivatives, got an A. So it's got good forces. If you go to the right, you see results and files. If you click on those, results gives a lot of details about what tests were done. And then the files is the raw data that was used. So you can actually look at it. In fact, some of these verification checks generate files that you can look at that can help you understand the potential. And then below that are the tests. So these are all of the computations that we've done on the system, you know, one after another. So here's the elastic constants cubic test, for example. it shows you it did it for BCC, FCC, and simple cubic. And if you click on this expand button, it'll show you the results themselves. Also, you can see on the right the benchmark time. So everything we do, we benchmark using an architecture independent measure. So we normalize everything by something called the whetstone benchmark. And so it gives you a time that you can compare across architectures. And so you can see, how slow different potentials are, or how fast. And so we have I won't show you this now, but we can then generate plots of accuracy versus cost. And so then you can maybe select which potential is appropriate given how much you can afford, how large your simulation. Let's say you have to make a decision. I can maybe pay some accuracy because I need a faster potential. Then we tabulate the information in a variety of ways. We visualize it in a variety of ways. And another thing that OpenKIM is about is that you can contribute your own visualizations. And so we aim to really be a platform that people contribute to. We create the infrastructure, and the idea is that people contribute their way of visualizing their potentials, their tests into our system, and we orchestrate it for you. Okay, so let me end here by kind of showing you how this works in practice and what this portability, usability, reproducibility, and reliability looks like when you use a potential in practice. So I'll show you LAMMPS and then briefly show you ASC. So if you want to use OpenKIM with LAMMPS, the first thing, like I said, is you have to install the KIMAPI and you have to get the potentials. And so if you're installing from binary, I already showed you, you would do something, so I should, no, actually I have to say something more here. So because we have these binaries now, we've integrated them into the installation binaries of other codes. So for LAMMPS, for example, LAMMPS is available as a binary. If you install the LAMMPS binary, it will automatically install the KIMAPI and bring it in as a dependency. And so there's nothing really more for you to do, except you can bring in the models. Depending on the binary packager, sometimes the models have to be separate, sometimes not. It depends on the details of how these binaries work. So for this particular platform, you have to do, for Fedora, you have to do LAMMPS and then you install the models. Or you can install from source if you're a developer, if you want additional features. And that's pretty straightforward. You download the code, you create a build directory, you do CMake, you make install, and then you're basically done. The last thing is, this is a KIM command, KIM Applications Collection Management, install system OpenKIM. That'll bring in all of our potentials and put them on your system. So this whole thing takes 5 minutes, 10 minutes, and you have the system. Okay, so now you have KIM on the system and you have LAMMPS that's compatible with it. And we've worked with the LAMMPS developers over the last few years to fully integrate this into LAMMPS. And so if you wanted to use, say, the Ercolesi-Adams potential, EAM potentials for aluminum, you would add, the only difference to a KIM script, to a LAMMPS script, are these two commands. You have KIM init at the top, which just says, I want to use this ID, and all you're giving there is the KIM ID, the one that I showed you before, and the units that you're going to be using, which are metal units. And then at the end, you have KIM interactions that actually activates the potential, and aluminum, that's the LAMMPS atom types to species mapping that LAMMPS requires. That's it. And then LAMMPS will just use this potential magically. In fact, LAMMPS, as I said, what actually happens behind the scenes is it links to the DLL associated with this potential, and they communicate through the API. And so now you see you've got the ID, the version number. You can go back, and if you did this same simulation 100 years from now, in principle, if we're all around and LAMMPS is around and so on, it would give you the same results. Modular things like operating system, things like that. If you run it, you get a result. This computes the cohesive energy of FCC aluminum. And if you notice that in this case, I just hardwired the lattice constant to 4.05, which is the experimental lattice constant for FCC. And it's telling me that, I compute the cohesive energy and pressure. The pressure is not 0. That's because 4.05 is not the equilibrium lattice constant for Ercolesi-Adams. And so how do you know what the real value is? Well, you could go to the paper and look it up, or you could go to OpenKIM actually and look up on our site, or maybe Atomistic Tools or wherever, and try and find that number. But one of the things that we've done is we've created this query interface that allows you to directly pull results for all of the predictions that are computed in the OpenKIM sites. And we have a large API with supported properties. You can go to this link if you'd like to see them. And what that means is that I would change my LAMMPS input script like this. I use another command that's incorporated into LAMMPS called KIMQuery. And if you remember, let me just go back one here. I had lattice FCC 4.05. It was just hardwired. Instead, what I'm doing now is I'm doing a query to put into the variable A0 the result of that query. And so when you put this line into LAMMPS, what it does, the get lattice constant cubic function activates a web query, goes to openkim.org, and it's asking for the cubic lattice constant for FCC aluminum in angstroms. That result is 4.032027, what, blah, blah, blah. That number is returned from OpenKIM and is put into A0. And then you would construct your lattice using that A0 number. And so then you know you're using the right parameter, and then you see the pressure is close to 0 because you're using the correct value. Okay, same thing works in ASC. The only thing is there's a KIM calculator in ASC. You would simply load it with these from commands on the top. And the model command defines which potential I want to use. It's not a definition, it's Python. I'm just defining a variable equal to this code, so I don't have to write that long script. And then I get A0 is equal to get lattice constant cubic. We have a query Python package called KIM Python utils that you see on top. And it simply executes that function. Again, it's doing a web query, puts the value in A0. And then on the next line, it says Adams face-centered cubic. I'm giving the lattice constant equal to A0, which I just got from OpenKIM. And then I'm defining calc equal to KIM model. KIM is the KIM calculator. Calc is now the calculator in OpenKIM, and the rest of ASC is standard. So that will work with every single potential in our system. All right, so that's basically what I'll show you. There's a lot more, but I don't want to go over too much. So the kind of current developments, where we are right now. Everything that I've described is available as a use that you can put on your own resources and run yourself. We have a Docker container that you can pull in and basically run these tests, bring in potentials, run verification checks, do your own development, etc. It's in beta, so you have to tell us, and then we'll give it to you. We'll be just putting it formally on our site soon. It's operational. We're just still making sure everything is good. We are also doing, we have a campaign that we're calling All in KIM. We are actively going out and reaching out to developers to incorporate their content into our system. So we are in contact with dozens of developers right now and working with them to upload content. It's very simple, actually. It's literally filling in an online form and providing parameter files, and you're done. It takes about, well, however long it takes you to prepare the information, the parameter files and the description and title. Uploading is 5 minutes. And so we're making good progress on that. We're working with some industrial partners on developing tools for industry. If you're interested in that, let me know. We've developed a fitting framework for machine learning potentials that sits on top of OpenKIM and uses all of this infrastructure to develop potentials and creates potentials that are compatible with KIM and can be uploaded if the developer wants to. We have, along the lines of what Yuri said, we have this sort of consumer report style comparison where you can choose properties, choose potentials, and do comparisons between them in a variety of ways. That's all in beta, not on our site yet, but will be soon. And as I mentioned, there's this other project, an extension of OpenKIM to chemical and biological force fields. It's a collaboration with the Charm GUI project and Hendrik Heinz, who developed something called the interfacial force field, and the OpenFF project. We're working with them to try and incorporate standards like this into the chemical biological world. So that's it. That's what I wanted to show you, and I'll be happy to answer any questions, or you can contact me at the information below if you'd like.